Welcome all. My name is Alison Costa. I am with the School of Mathematics and Statistics of the University of Melbourne, and I will be your host today in this ACEMS virtual public lecture, Optimal Decision Making, a tribute to female ingenuity. I want to acknowledge the traditional owners of the land on which I live and work, the Wurundjeri people of the Kulin Nation, who have been custodians of this land for thousands of years. I pay my respects to their elders, past and present, and to Indigenous communities joining us online today. Well, we all join online today. What incredible things are these computers that allow us to meet in the middle of a pandemic? But as you know, it's not only the computers that allow us to be here. Maybe what's really connecting us today are the algorithms, the code that run into these computers. Today, we honor the first person to write such a code, Ada Lovelace. Ada Lovelace was born in 1815, daughter of the poet Lord Byron and mathematician Anne Milbanke. It was through her mother that Ada herself became a mathematician and got introduced to a circle of mathematicians, one of which, Charles Babbage. Babbage was developing a sort of primitive computer, but he kind of looked at it more like a calculator. Ada was the one who looked at his machine and saw, oh, it can do more, and then wrote some code for it. Today, to celebrate Ada Lovelace Day, we have the pleasure to receive two women who have done exactly the same thing. They have looked at algorithms for mathematical optimization with a fresh and new perspective. And by doing so, they have extended and continue to extend the limits of what we think is possible in mathematics and computer science. The first of these mathematicians is Alison Harcourt. Alison completed a Bachelor of Arts with honors in 1950, a Bachelor of Science in 1952, and a Master of Arts in 1958, all in the University of Melbourne. She then spent a period at the London School of Economics, where she worked with her colleague Ailsa and developed a method called branch and bound, which built upon the groundbreaking simplex algorithm for linear programming proposed a decade earlier by George Dantes. But her method, the branch and bound, could solve a broader class of problems than the simplex algorithm, a broader and more flexible class of problems known as mixed integer programs. After this time in London, Alison came back to Melbourne and started studying other problems, making significant contributions to other areas, from working in a methodology to quantify poverty in Australia to examining the Australian electoral system, which resulted in a 1984 amendment to the Commonwealth Electoral Act. Meanwhile, her branch and bound method took a life of its own. Nowadays, it's taught in any science, technology, engineering, math university around the world, and it's the algorithmic backbone of all modern optimization engines for mixed integer programming. In 2018, Alison received an honoris causa doctorate degree from UniMelb and was named Victoria Senior Citizen of the Year. In 2019, she was made an Officer of the Order of Australia in recognition of her, I quote, distinguished service to mathematics and computer science through pioneering research and development of integer linear programming. What a privilege to have Alison here today. Also an honor is to have Professor Kate Smith-Miles. Kate's alma mater is also the University of Melbourne, with a Bachelor of Science honors in mathematics and a PhD in electrical engineering at the university. Kate started her career at Monash University in 1996, and since 2017, she's back at UniMelb at the School of Mathematics and Statistics as a professor of applied mathematics. She's also a chief investigator of ACEMS, associate dean for enterprise and innovation, and an Australian laureate fellow at the University of Melbourne. Kate's multi-award winning research has the same flavor as Ada's and Alison's. It is with ingenuity and passion that she combines and unifies knowledge in optimization, mathematics, statistics, machine learning, to solve problems in fields as diverse as manufacturing, epidemiology, computer vision, finance, among many others. Her most recent project is, as usual for Kate, a very ambitious one. Kate is the director of and the main force behind Optima, an ARC training center, which goal is to reshape the whole landscape of optimization applied to the industry in Australia. bringing together the different branches of optimization in academia and taking them where they are most needed, in society, in industry, in public decision-making. Optima is just starting its operation, but with the leadership of Kate, I'm sure we will hear about it for years to come. So, with no further delay, it's with great pleasure that I invite Kate to start guiding us through this public lecture, Optimal Decision-Making, a tribute to female ingenuity. Please, Kate.
Thanks very much, Alison. It's a great honour indeed to be able to pay tribute today on Ada Lovelace Day to some remarkable women, not just Ada Lovelace herself, but Ailsa and Alison Doig, now Alison Harcourt, who will join me soon. So the plan for today is that I'm going to take you through an overview of what is optimisation and how it impacts our lives. You can see from the screen many examples of how optimisation impacts our lives. Optimisation I'll formally define in a minute, but basically it's the mathematics of optimal decision-making. And I'm not talking about trivial decisions like whether I should take an umbrella when I go for a walk today. I'm talking about decisions where there are many, many choices and there's a right answer, but we need clever methods for how we can filter through the many combinations to try to arrive at the optimal answer. And we're talking about important decisions where even a small improvement in the decision could have a significant impact in financial terms, but also in saving lives or saving time. Optimization techniques underpin many of the decisions that we make every day as individual people, whether it's how to get from A to B with Google Maps or decisions that corporations make, mining companies. Certainly it's all about saving money, but also lots of public benefits like optimal use of limited hospital resources, for instance, or how to generate more renewable energies. So, I basically covered how optimization impacts our lives. Soon we're going to talk about a brief history of some of the breakthrough ideas leading up to the seminal work of Ailsa and Alison. And then we'll cover some of the future challenges in optimization. We'll hear directly from Alison after I've given this introduction. So that's the plan. So what is optimization? Well, everyone has seen optimization. This is a public lecture. So, this is based on high school foundations. Back in high school, everybody who studied calculus understood that when you're minimizing a function of one variable, suppose I have a variable x and I have a function f of x, and the function might look like this blue line, and we are basically trying to find the value of x that minimizes this function. And so here we have, this looks like an order 6 polynomial. It's got a couple of minima, and we call this one down here around x equals 70 the global minimum, and over here at x equals about 110 would be a local minimum. And we're trying to find the minimum function, and with calculus in high school we learnt some techniques for doing that. We find where the gradient is 0. We take the derivative and we set it equal to 0, and we find the stationary points. So let me put this in a more practical context. Suppose the decision we're trying to make is the number of items of some product we want to stock at a supermarket. So you run a supermarket and you're trying to decide how many items to purchase, say bags of corn chips. This is a lunchtime lecture. There's going to be quite a few references to food in this lecture. And so suppose f of x is the cost. So we might buy a certain number of bags of corn chips hoping to sell them, and it costs us a certain amount. And the more we buy, maybe our costs come down because we start to sell some. And as soon as our costs turn negative, we're in the profit zone. We can start to make a profit. So we want to make this function as small as possible. So how many bags should we buy to maximize our profit? And you might think it should just be monotonically decreasing, but life is complicated, and we might find that this item is perishable. And so you don't want to buy too much. It might go off before the use by. And you might also have storage costs if you purchase too many. And so we end up with a nonlinear function. So if we level up from this basic example and we consider not just one product, but supermarkets have many products. Suppose we have a function of 2 variables now. Well, now we're trying to find the values of x and y that minimize this bivariate function. And the darkest blue here is where you get the optimal combination of x and y that minimizes our costs. And so now it might be bags of corn chips and jars of salsa, for instance. So let's keep leveling up to try to reach the real world. The stuff we learnt in high school isn't going to help us. Calculus won't find the exact solution unless that function is really nice and, like we find in the textbook, nicely differentiable and not too not with such a high order polynomial. So we need numerical methods to approximate the optimal for very nonlinear functions, things that can't be differentiated or are discontinuous. And there's also usually a lot of rules, lots of constraints on the values that are allowed for these variables. So, for instance, we might have rules that restrict the domain. We might have some limits, some mins and maxes on the values that we want to consider. We might have other rules that they follow, business rules, for instance. You might know that, half the time when someone buys corn chips, they also buy salsa. So you might say that I want my number of jars of salsa to be at least half the number of bags of corn chips, and I've only got a certain shelf capacity for both of them. And you might also realise that it doesn't make sense to come up with an answer that says you should stock 72.3 bags of corn chips when bags of corn chips is a whole number. So what if the decisions have to be whole numbers? And that's a really important question for what we're talking about today, because the work that Landon Doig did enables us to solve optimal decision-making problems where the numbers have to be whole numbers, the answer. I was discussing this with my 16-year-old son, who said, why don't you just round the solution to the nearest whole number? It's a great question, and we'll see later on that rounding isn't going to give you necessarily the optimal or even a feasible solution. That's why some clever mathematics was needed that Alison and Ailsa developed. So here we have the tree of optimization techniques. Field of optimization really is broken down into, first of all, whether the decision variables are numbers that are continuous numbers or discrete numbers, whole numbers. And then we have considerations about whether there are such constraints on what they are allowed to be. So before World War I, the stuff you learnt in high school is what existed. The field of optimization was defined by these pre-World War I methods that you still learn in high school. So let's talk about those briefly. So back in the 17th and 18th centuries, all the way up to World War I, optimization was pretty much some techniques that had been developed in response to pressures in society, namely war. Wartime, it will be a recurring theme in this lecture. When we have urgent needs in society, we respond, mathematicians respond and develop some techniques. So we had Galileo and Newton, for instance, studying projectile motion. Where are the cannonballs going to land? And Newton claimed that he had developed a general method whereby I can calculate curves and determine maxima, minima, and centres of gravity. In other words, calculus. Of course, there's some controversy about whether it was Newton or Leibniz who actually invented calculus. They both were simultaneously working on the same ideas. That will also be a recurring theme in this lecture, because many great ideas simultaneously get progressed different places around the world. But regardless, Newton said, I can calculate the motion of heavenly bodies, but not the madness of people. He didn't want to weigh into all of the debate. It was all about modelling the physical world. Taking us all the way up to World War I, we have Geoffrey Taylor, who was a mathematician but also a pilot in the war, and he studied parachute dynamics to optimise landing locations. So this kind of calculus, parabolas, all this kind of stuff we learn in high school was pretty useful for a long time. Then we get to World War II and we see a new kind of mathematics emerge. And this was the mathematics of decision-making, nothing to do with where a cannonball is going to land. It was much more around how we have efficient and optimal operations. So here we have a war room in London during World War II. Notice all the women around here. There's also some women up here as well, supporting the men, and they're making decisions around things like which troops should be sent to which battles, which weapons should be allocated across the army, when should you do maintenance on planes and ships. All these are critical decisions, and calculus can't help you. It's a new kind of mathematics that's needed to answer these kinds of questions. Ultimately, optimal decision-making is about maximising or minimising some objective, something you care about, simultaneously satisfying some limits on those variables or some constraints or rules on those variables. That's what optimisation is all about. And this field really emerged in World War II, the field of operations research. So what we teach these high school and first year university calculus-based methods for continuous unconstrained optimization. But as soon as we start talking about these constraints, there are rules that limit the values that these decisions can take. And if we also have some conditions on what the nature of those objectives are, then we encounter the kinds of techniques we teach maybe in second year university around the world, linear programming. This part of the tree over here, we'll get to that. That's Alison and Ailsa's contribution. But for second year university, we teach linear program. So linear programming is just a special case of an optimization problem that involves continuous variables where the objective of the thing you care about depends linearly on those decisions. And we have linear constraints, either equality or inequality constraints. So mathematically, it looks like this. We're trying to minimize some linear function of our decision variable x, subject to some linear constraints. And these linear constraints are really, we've seen this in high school as well, just a bunch of simultaneous equations defining a feasible region. So as long as you choose an x within the feasible region, the question is which x gives me the minimum objective function. And despite the name, linear programming is not about computer programming at all. In fact, it will be decades before computers could solve linear programming problems. So there are a bunch of breakthrough ideas in linear programming that I want to take you through just so that we can really appreciate the breakthrough idea for integer programming when the decision variables have to be whole numbers. Linear programming was independently discovered 3 times over a 10-year period by Russians and Americans studying these sort of resource allocation problems motivated by wartime. All of these men received major prizes for their breakthroughs. We have Leontief and Kantorovich and Koopmans all receiving Nobel Prizes in economics. And their foundational work gave inspiration for George Dantzig when he developed a method for solving linear programming problems when he was working at the US Pentagon. Here's a picture of Dantzig receiving the National Medal of Science from US President Gerald Ford in 1976 for the mathematical technique he developed in 1947, known as the simplex method. So these men have received great accolades for their breakthroughs. George Dantzig's challenge from the US Pentagon was, again, a wartime challenge. How can mathematics be used to make optimal decisions to deploy Air Force resources, that's people and equipment? But back then, it was only desk calculators and they had some IBM accounting equipment. So how can we make optimal decisions? There are so many combinations to go through. We've got limited resources. We need clever mathematics to help us prune back that search space. So he took some of the earlier ideas of Leontief 10 years earlier on linear programming formulations, and he developed mathematically for the first time this class of optimization problems called linear programming that we saw before, minimize this linear function subject to some linear constraints. And he worked out how to solve them efficiently. So the simplex method was proposed in 1947, long before we had computers. Let me give you an example of the simplex method in action. So we have Stigler's diet problem. So in 1939, the problem was posed, how do we feed an army of men for minimal cost while meeting essential nutritional requirements? And so we have this poster here with the army saying, food is ammunition, don't waste it. Right? If we can save money on how much it costs to feed the army, that's money that can be invested in other efforts for the war. So in 1939, this problem was posed. Stigler formulated the problem as a linear program. He didn't know how to solve it exactly, but he formulated it mathematically. So we have 77 variables, and these are our available food choices. So 77 types of food that the army was prepared to feed the men. 9 nutritional rules about minimum amounts of iron and protein and things. And Stigler came up with a solution that cost $39.93 per man per year. He didn't know how to solve it exactly. He didn't know how to mathematically prove that this was the exact answer. He came up with some trial and error solutions, and he came up with a diet, and it was pretty accurate, because after the simplex method in 1947, when we actually had a mathematical technique to prove what the optimal answer was, the optimal solution was found to only cost 24 cents more. So Stigler's guess was pretty good. But look, it took 120 man days of hand calculations. Not sure how many woman days that would have been, but 120 man days of hand calculations to prove what the optimal solution was, because they didn't have computers yet. So that was 2 weeks of 9 people working full-time to crunch through the answers with the simplex method that made it feasible to do so. So when we talk about the Stigler diet, we also have to consider palatability, of course. There was no constraint for palatability. It's all about nutrients. George Stigler won the Nobel Prize in 1983, not for his diet problem, but for some other stuff that he did. The diet problem, though, has had a huge impact on the world since. So here's the table of nutritional requirements for Stigler's diet problem. How many calories the men were supposed to have, how many grams of protein and calcium. So these are the rules, 9 rules that must be satisfied. And this is the solution. Stigler's diet in 1939, the solution he came up with said each man should be given 57 cans of evaporated milk and 285 pounds of dried navy beans. And the total cost of supplying them with these 5 items is $39.93 each. Now, the optimal solution in 1947, when the simplex method was proposed, and we know for sure what the optimal solution was, the one that was 24 cents cheaper, it actually replaced the evaporated milk with beef liver because it was actually better bang for its buck. But Stigler didn't stumble across that solution with his trial and error. So just as an aside, you may be wondering if it's possible to actually eat well with those 5 ingredients. This is a lunchtime lecture. Let's talk food just briefly. Stigler actually said no one recommends these diets for anyone, let alone everyone. And others have said that this least cost diet is the equivalent of a human dog biscuit. But the chef at Google took on the challenge of designing a meal with these 5 ingredients. It's called Foie Linéaire à la Stigler, and it's basically some fancy stuff he's done with the beef liver. So I don't know if they still serve that in the Google cafeteria, but very interesting outcome. And if you want to play around with this, there's websites you can go to where you can create your own optimized menu. You can type in the foods you want to consider, and if you don't want to have any at all, you put the max to 0. You can, if you want to insist that you have a certain food, you can increase the min. You can type in your nutritional requirements between a min and a max. And it has all the data in there about the nutritional requirements, and you can solve and get your optimized meal. Look, I don't think this is recommended for humans, but it should be noted that this diet problem was the precursor of a whole heap of successful linear programming applications. You can imagine how you would use similar ideas to figure out how to efficiently feed cattle and other animals in farming, how to mix fertilizers, basically any kind of mixing of ingredients problems to satisfy some rules. So it's had great success. The idea of minimum cost diets for humans also gave baselines for government funding for school lunch programs, for instance. So it's been quite useful. But of course, we have a problem with this whole number decision variable issue. The cans of evaporated milk, that's a whole number versus the continuous solution, which was in terms of pounds of liver. We really do need to be able to deal with problems that with the solution has to have a discrete whole number. So let's visualize all of this so we can really appreciate Ailsa and Alison's solution to this problem. I'm going to make it easier to visualize in 2D by generalizing to a multivitamin problem. Suppose we have 2 multivitamins and we're trying to decide how many we need to meet these requirements. So a nutritionist has told us we have to have a certain number of milligrams of iron and B1 and B2. And we have 2 brands of pill A and pill B. And each pill we know how much it costs. 67 cents for brand A and $1 for brand B, and we know how many grams of iron B1 and B2 are in each pill. So this is similar to the Stigler diet problem, but we've only got two choices, which means I can show you some 2D pictures and you can appreciate exactly what linear programming does, and then also what Ailsa and Alison's branch and bound method does. So let's use this as an example to illustrate. So how many pills of each brand should be bought each month for the cheapest way to meet nutritional requirements? And we can't cut open these pills. It has to be a whole number solution. Okay, so if we relax that integer rule and we allow a fractional solution, we can solve this using linear programming. So we have some resource requirements. We have decision variables. X1 is the number of brand A pills and X2 is the number of brand B pills. And our objective function is to minimize the total cost. It was 67 cents for brand A and $1 for brand B. So that's our total cost. We have some constraints in terms of the total amount of iron we have to have. So pill A gave us 30 milligrams and pill B gave us 10. So if we multiply by the amount we're choosing to buy, it has to be at least 2,400 milligrams. Similar rule for B1 and B2. And of course, we need these to be positive numbers. So mathematically, we can write this as minimize something subject to something. And we get these coefficients of C, A, and B in these matrices and vectors. So that's how we would write it out as a linear programming formulation. Now, because it's 2D, I can just show you how simple this is. This is high school stuff. Each one of these constraints, you can rearrange it in, y equals mx plus c. You can rearrange it to get x2 by itself and everything else on the other side. And you can recognize that I have 3 lines defining my rules. And the feasible region is the area that satisfies all of those rules. So this is very similar to, what I help my children do with their high school homework of I've got a line and the inequality tells you which side of the line you have to shade. So we have this feasible region. If this is the number of brand A, X1, and this is the number of brand B, X2 pills we're going to buy, you can pick a number, a combination anywhere in this feasible region, and it's a valid solution. It may not be a minimal cost solution, right? The cheapest cost we have to find, but it has to be somewhere within this yellow feasible region. So we can find these points of intersection. Again, that's high school stuff, to identify the boundaries of this feasible region. And we can evaluate the objective function at all these vertices of the feasible region. And the simplex method tells us that the optimal solution is at a vertex point. So if I evaluate the cost of each of these vertex solutions, if I buy no brand A but 240 brand B, it's going to cost me $240 a month. If I buy 300 brand A and no brand B, it's going to cost me $201 a month. And B and C are around $140 each. B is optimal, but notice B is not integer. It's fractional. I can't have this. I can't have 42.8 brand A pills. So the optimal solution is feasible in terms of when I relaxed the integer requirement, but for the real world problem where I need it to be a whole number, I can't use this solution. Is there another solution somewhere in here that is minimal cost and whole number integer? That's the question. So there's the minimum cost. And when we look at the objective function line, it's just another line in the space, and the costs are increasing as that line moves across the space. So this is the minimum cost at B, and if I move this line across the space here, the costs are only increasing. So I can choose a point way out here, but it's going to be much more expensive than if I choose the minimum cost point. So remember, we relaxed that integer requirement so we could use linear programming, or so we could visualize the linear programming vertices here. But we really do care about that integer requirement. So the simplex method that George Danzig invented in 1947 was really just giving an efficient rule for how to search through those vertices. If we can find all the vertices of the feasible region and then calculate the objective function, the best one is the optimal solution. But the number of vertices can be really huge for real-world problems. And so we need to find some clever techniques that can avoid wasting time finding infeasible intersection points, and also wasting time evaluating vertices that aren't going to improve the best solution we've found so far. So how do we know which vertices are going to be wasting our time? The simplex method gives us a rule that guarantees we find the optimal solution by moving intelligently around the vertices until it can prove that it's found the optimal solution, and not wasting time exploring ones that it can prove are a dead end. And that was a prize-worthy idea. It's a very clever idea. And it provided a long-awaited breakthrough. So George Dantzig moved from the Pentagon to the Rand Corporation in 1952 to focus on computer implementation of his simplex method, because by then the broader industry applications were really clear. It wasn't just military and government that were interested in this, but industry was also super keen. So just as an aside, in 1953, he managed to get a computer to solve Stigler's diet problem in 8 hours of computation instead of 120 man days. But this won't help find integer solutions, and rounding a fractional solution isn't necessarily optimal. So how are we going to find those optimal integer solutions? So let me just quickly show you that, that rounding isn't going to help. So the optimal integer solution may not lie at the vertices. So C down here is whole number, and costs 39 cents more than the fractional solution. So you might think C is looking like the best answer here. But what about if we rounded B? What if we round, instead of 42.8, what if we considered 42 or 43? Instead of 111.4 brand B pills, what if we went 111 or 112? What's rounding going to do? That's what my son was asking. Why not rounding? So here we have an illustration, just a zoom in here of the point B. And if we consider the 4 rounded points are rounded, all of them whole number solutions. And what I can tell you is that these 3 are infeasible. They're not in the yellow zone. They're going to round to an infeasible solution. There's only one rounding each of them up that gives you a feasible solution, but it's more expensive than point C. It costs $140.81, whereas point C costs $140.40. So rounding can create infeasible solutions and may not even be optimal. So that's an answer to my son. Rounding is not necessarily going to give you what you're after. We need cleverer methods. Okay, so if the variables must be whole numbers, rounding the LP solution gives us integers, but it's often suboptimal. An integer solution is never going to be better than the fractional solution. That's the price we pay for adding an extra constraint, the integer requirement. The lower bound on the optimal integer objective is provided by the linear programming solution. We can't do better than the linear programming fractional solution. And the upper bound is the best integer solution we've found so far. So far we've found C was the best integer solution, and we know the lower bound, but the question is there something in between? How can we find it? So we need a clever method, and that's where we get to the work of Ailsa and Alison. So we have this paper in 1960 that they published, an automatic method for solving discrete programming problems by A.H. Land and A.G. Doig. We'll talk to Alison in a minute about their decision to not mention their first names because they were women. But basically, this paper has had a profound impact. Around 4,000 citations. It's really hard to get an accurate estimate of this, but over 2,500 citations since this anniversary book was published in 2010. So basically now, because of this method we have for integer programming, this is what we teach in universities now. These 1960s methods we teach in third year. So we're expanding the tree. The basic idea of branch and bound is also divide and conquer. The idea is that we divide the original problem into smaller and smaller subproblems until each of those subproblems can be conquered. And so the dividing we call branching. We get these partitions, these subsets of the space. And then the conquering is where we use our knowledge about the upper and lower bounds to decide whether or not the optimal solution could possibly lie there. And if it can't possibly lie there, then we don't waste time searching that part of the tree. So you end up with a tree structure like this. So this is an extract from the original 1960 paper. And Alison can talk to us more about this, but basically they were solving a 21 variable problem with 6 constraints, and it involved solving 37 linear programming problems. And they've drawn this by hand, and I suspect they solved the linear programming problems not using a computer. So there's a lot of labour that's gone into this. We can talk to Alison about that in a minute. So returning to our multivitamin example then, let's see how this tree gets constructed. We have linear programming problem number 1 that gave us the fractional solution. We can't use that solution, but it gives us a lower bound. We know the solution, the real solution that we can use is going to cost at least $140.01. And we have an upper bound from point C. So far we have a solution that costs $140.40, but the question is there something in between? So every time, we create this tree of problems. So I can't have 42.8 brand A pills, but I could have 42, or I could have 43 or more, 42 or less, or 43 or more. But let's get out of that fractional space. So we create linear programming 2 and 3, and we solve those. And we find this one is now feasible. It's integer, but it's not better than what we already had with point C. And this one is still fractional, but it's within the bounds, and so we can continue. And so we now branch. Instead of 111.3, we go make it less than 111, or make it more than, sorry, that should be 112. And this is within the bounds, so we continue. This is feasible but not better. We continue on this one, take this 43.8 and make it less than 43 or more than 44. That's infeasible. As you continue down the tree, we finally get to this one here, which is feasible and better than the point C. So we found a point that's integer and better than point C. And so this is the optimal point, and it wasn't point C. We found a solution that was better. If we just look at what happened with that sequence, our original solution to the linear programming problem was point B. The sequence of points we're exploring in this space are these red dots. So we solved linear programming 2, and we got a solution that was integer, but it was up here. It was feasible, but it's maybe not the cheapest. And so look at the red points that get explored as we traverse this tree. And you can see that the optimal solution is this one here. And it's in between the original linear programming solution and the solution provided by point C. So the branch and bound method has helped us systematically explore, without wasting any time, explore where the optimal solutions lie, and get an optimal solution. So Alison's going to talk to us about some of the advances that happened, but basically their method worked its way into the first commercial code in the mid-1960s by the Rand Corporation, and there were lots of industry users in petroleum industry and the military and the coal board. There were some further advances in the 70s and 80s. Another woman at British Petroleum developed improved methods for how you select which variable to choose to start with. And we have lots of advances as computer hardware continued, noting that in 1988, AT&T patented an improved method for optimization and paid $8.9 million for it. So it's big business. We have commercial code that's made its way into software that is available today, including Cplex and others. So the impact of branch and bound today is that it's the basis of all of the commercial solvers that are on the market. It's a very active area of research as well, with additional challenges that researchers are still tackling today. If you search for branch and bound in Google Scholar, you'll get over 3.5 million hits. So it's a pretty hot topic. So now it's time to hear an eyewitness account from Alison. I've asked Alison to think about answers to these questions, things I'm curious about. You'll be curious about other things, and you can write those in the Q&A chat that we'll get to at the end. But I was interested in, where did this idea come from? How does a girl from country Victoria come up with this idea? What was her motivation? And tell us about the inspiration and perspiration. The challenges of publishing and promoting the idea, noticing that it was 2 women that used their initials, not their first names. I'm curious about that. The impact of the idea in academia and industry, and whether she was paying attention and aware of that. And I know she went on to work in other areas, but her thoughts about that. And finally, Alison did receive some recognition. Here's a newspaper article in about 1965 but it wasn't for the branch and bound method. Since then, of course, she's received her honorary doctorate in more recent years and had some media coverage and other things. And so there's some long overdue recognition that's finally come, and I would just love to hear how she feels about all of this now. So, Alison, over to you.
Hello, everyone. This is Alison now. And how did I come to statistics? Well, I say I came in by the back door. My original course at university was to do maths and physics. Physics was more of a handful than maths. I needed 2 years to get through physics 3. And in that second year of doing physics 3, I picked up statistics because I just wanted to see what it was about. Well, it was just suited me down to the ground. So I stayed with statistics and went through the subjects of how much of that was available at the time. Now, this was, I was sort of wondering what to do with a master's topic, but then there was a lovely intervention for me, because Bob Dean, who was a Melbourne engineering graduate, he had gone to Bahrain to work for the company which eventually was called British Petroleum. I think it had a more complicated name at the time that Bob went. But he came back on leave to Melbourne, gave a talk to the statistics department in which he talked about this grand new technique called linear programming. And he was very enthusiastic about it, because one of the problems with oil wells is that the oil that comes from the well has not been nicely separated for you. It's up to you now to fractionate that oil into the sort of the heavy components, which will be good for commercial, so to speak, land things, and the light components, which you can use for airplane fuel and that. And Bob said that there was this new technique called linear programming, which just suited them down to the ground. He said also, we thought about trying to use linear programming for scheduling the movements of tankers from Bahrain to all over the world. This was at about the time of the Suez crisis, which was an added complication. And he said the trouble with using the sort of working with ships is that the answers came out that you had half a ship going to Cape Town and the other half ship going over to Perth. And he said, it would be helpful if we could get it to give integer answers where we need them. Well, Professor Bells and I sort of talked about this, and he noted a paper from a paper mill. And this was a trim problem. In the manufacturing of paper, the first product is an enormous roll, about 8 feet long, and that then has to be sliced as the papers are rolling off the manufacturing, the sort of furnace. They've got to be sliced into rolls of appropriate commercial width. And naturally enough, there's going to be some cut-off sort of trim. Going back to previous things, an 8-foot roll, you might be able to get sort of 2-3 foot rolls from that, but then you've got 2 feet left at the end that's going to be waste or trim. And obviously the manufacturers want to minimize the trim as much as possible. Well, that was that seemed like would be a good thing to try with have a look at the linear programming aspects of this problem. And well, I took it away and thought about it, had an idea, mentioned it to the professor. He mentioned it to Professor Maurice Kendall, who's the head of sort of one of the top people at the London School of Economics. And Professor Kendall said, well, we've got some people working on linear programming. Why doesn't she come to London and join them? So moved to London. Now, the foundations at that time, we've mentioned George Stansig, and you've seen from Kate's lovely talk how relevant his work was. He was tremendous, and there were a lot of mathematicians following on the ideas. And George Stansig, in fact, published a paper in Econometrica, sort of saying, please, please, somebody tell us how to get integer solutions. And I was not aware of this, but there was a man called Ralph Gomery in the United States who had also sort of seen this problem. In fact, several of the American mathematicians had looked at this problem with respect to that, and Ralph Gomery published a sort of an introductory paper in 1958, and then in 1960 he also had a paper published in the same issue of Econometrica as the one you saw the heading of it earlier, in Kate's showed you. Well, Ralph Gomery also had his cutting plane approach. Now, this cutting plane approach is, I have to say, much more elegant. I almost blush when I think how simple my notion was for getting integer solutions. Ralph Gomery's method was much more elegant, but he didn't supply any illustrations of how it works in practice. And now, whom did I meet at the London School of Economics? Well, they had already been tantalized by this notion of linear programming, and this well-known class of problems called the traveling salesman problem. Now, that's about somebody who has a large number of elements to deliver. In Ailsa's case, this was delivery of coal and coke from the mines in northern England to all other sort of towns and villages down in the south, and what was the best route for the salesman to take when they were delivering the coal, to minimise the cost of delivery and meet the requirements for coal and coke from the different sources, different cities and towns. And so then I turned up with this sort of notion that I had that I could modify a linear program to provide the integer solution. So Ailsa and I worked on this because we just wanted to make sure that it covered all the requirements were met. And it turned out that this went very nicely. It's a very, very simple, the initial idea is very simple. It has been developed in a way that goes beyond my understanding, but it went well. Kate was wondering why we used our initials rather than putting it in as work by Ailsa and Alison. Well, apart from the difficulty some people have with spelling Alison, which, you know, I've got an example here. Look, there's Alison Costa. So, but we thought that coming from the United Kingdom, submitting a paper to a US journal, and knowing that sometimes women don't manage quite so well. We thought we would disguise it. So how were they to know that A.H. Land was a really competent English mathematician and that A.G. Doig was a mathematician from that funny little island over in the Southern Hemisphere? It went very well. Now, futures, what happens next? Well, I can see the slide up there. I'd like to say that Ailsa continued. She continued and expanded her studies. It was just at the time when computers were coming in, and they were just made work so much better. So she was able to work and did terrific work. A wonderful person to collaborate with. I really sort of enjoyed my time there. Even one time, a couple of years ago, I'd been invited to go and talk to the students at my original primary school, which was Colac West Primary School. So I went up and gave a talk to the senior students there, and I spoke to Ailsa at that time. I just phoned back and heard what news from her. But the reason I went back to Australia was because the Prime Minister at the time, Professor Robert Menzies, it became brilliantly clear to him that the universities were in a bad need of more support and money. He gave generous endowments to all the Australian universities so that they could increase the number of students so that they could increase staff. And I was one of that increased staff. So I went back to Melbourne. That was in 1963. Our paper had been published in 1960. So it was sort of, there didn't seem to be any interest in it in Melbourne. And I sort of returned to statistics, lecturing in statistics, and a couple of other major things. I participated in Ronald Henderson's first poverty survey of poverty in Melbourne, and then subsequently with Dr. Malcolm Clark, we were able to persuade the federal government to consider to adjust the part of the election law to make it a little bit more honest in its use of randomisation. So that's the sort of story for Alison Harcourt. But for branch and bound, our method got that name in 1963 from one person who suggested that was a good name. And that has grown and grown. I'm overwhelmed when I look at what has been developed from it. I think Montgomery's method has also had a lot of following, but it was never as presented sort of good for numerical work. It looked great on paper, but the branch and bound or Doig method gave you actual numerical answers. So that's my turn. That's it.
Thank you, Alison. That was wonderful to hear your eyewitness account of all of that. And I'm sure there'll be lots of questions. I know we're running out of time, but maybe we can stay on for the people who'd like to ask some questions. Let me just close by saying that just like we've seen throughout this story, where industry really has driven a lot of the demand for advancing mathematical techniques to be able to make optimal decisions, we continue that with Optima, our new centre where we have a lot of industry collaboration. So
I encourage anyone who's interested in that to go to our website and check out there's an introductory video about what Optima is all about, but it's very much continuing in the spirit of this, just like British Petroleum and other organisations really helped support advances in optimisation that Alison was part of. This continues into the future. So thank you, and I'm sure Alison and I would be very happy to answer any questions.
Thank you, Kate. Thank you, Alison. That's really an honor and a privilege to be here listening to you. There is a lot of praise for both of your participations in the chat. There is praise for your T-shirt, Alison. If you could just tell us what it says for those who cannot see it.
Oh, my beautiful T-shirt was a present from one of my nieces, and it says, now I'm trying to read it upside down.
I think it says, never underestimate an old woman with a mathematics degree. Is that right?
That's right, yes.
That's amazing. There is one question in the chat, Alison. We all know you received a lot of recent recognition for this amazing work that you did throughout your career. Do you feel it took, I definitely feel it took too long for this recognition to be given. How do you feel about that? Did you ever think of that when you were before, or what's your impression on that?
Well, I think it was goes back to a certain lack of cooperation within the University of Melbourne at that time. Not in sort of, it's improved a lot in recent years, but back in the sort of early 1960s, there was mathematics, but you might, so to speak, say hello to an economist, but you didn't do very much else. The mathematicians were much better in collaborating with the science faculty, but there was very little cross recognition between economics and mathematics. And that's why I think there was not much recognition there. And also it just was the sort of growth of the universities from about 63 on. A lot of the staff were just held, sort of all their time was taken up with more teaching, and there wasn't a lot of time for collaborating and working on other problems.
Well, I'll just say that back in like the late 1980s and early 1990s, when I was an undergraduate student learning operations research in the department, none of my lecturers told me that you were down the corridor. They never told us about this inspiring story, and it would have been so wonderful to have had you come and give guest lectures and things. But yeah, it's a mystery to me, and it was so fantastic that we managed to finally get some recognition for your efforts.
I think there was.
Oh, you're muted, Alison. Yeah,
Oh,
there we go.
Yes, I just think that they sort of weren't curious about what others had done.
Yeah, no, the impact has been profound, and it's so great to recognise that now.
Talking about your impact goes, even though, of course, for the world, the branch and bound method has the impact that it has, but for our community, you definitely have an impact that went through all these years as well. We have a message from Michael McCarthy, who said that he was in your statistics class in 1987. And I just wonder if you have any idea of how many students have you tutored and taught in all your years of your career?
Oh, a lot. I'm sort of very much delighted when somebody comes and says, remember me, I was in your sort of stats too, you know, back at such and such a time. And I think I'm very proud of the fact that the Australian Bureau, ABS, Australian Bureau of Statistics, the deputy head at the moment is an ex-student of mine. And indeed, I did also tutor and lecture to Dennis Truan when he was head of the ABS. So they're there, and they're also down in the Children's Hospital. The leading statistician in the research down at the Royal Children's Hospital is also an ex-student of mine. And I haven't counted the others, but those are the ones that I remember with sort of great pride. Oh, I forgot. There's one extra who married, went to England when her husband was on study leave. She got sort of was a bit bored, so she trotted along to Oxford and got herself a job there. And subsequently, I'm pleased to say that she is now a fellow of the Royal Society. So that's didn't get to the FRS myself, but so did it, but Eleanor did.
We'll have to nominate you, Alison.
Oh, yes, yes.
We are running out of time, but maybe one more question that from the chat. If you, both of you, have any comments on the role of mathematics teaching today, how has it changed, if it has changed at all, and where are we headed in terms of teaching mathematics?
Alison is muted. I don't know if she's responded. Yeah.
Well, the teaching of mathematics should begin early, about three or four. I sort of found my feet in mathematics at kindergarten, where I loved the sort of simple sums that we were doing there. And then it continued, you know, it was sort of, well, consolidated in 6th grade when our 6th grade teacher picked up the chalk and started drawing, and he drew a beautiful triangle. And guess what he taught us? He taught us Pythagoras' theorem, did it geometrically there. Just a wonderful demonstration of that important theorem. And that stayed with me all my life. I mean, you know, you will find Pythagoras' theorem almost everywhere. You can trip over it and still enjoy it.
I think it's fair to say that Alison was a bit of a prodigy as a child, right? Alison, you skipped some grades in school and you found mathematics very easy. Not all students are like that, of course. And I think the high school and primary school curriculum can be a little bit uninspiring and a little bit removed from students being able to see the real world applications. And as you saw in my lecture, a lot of what we teach in school is very 17th, 18th century up to World War I, parabolas, cannonballs. It's hard for students to see the applications of where this could go. And yet it's so foundational, and it leads to some of the things that we were talking about today. The stuff I talked about it's all extending on basic high school ideas. And yes, I know some of the general maths or whatever it is gets to some of the foundations of linear programming, the graphical method, and, you know, being able to see that. But it's just like a little push further, and the students could really appreciate some of the real world applications of the mathematics they're learning.
Yes, and I'm sure we could all appreciate today's talk and see that, as you say, Kate, sometimes the test of time for brilliant ideas is that when they get pushed from graduate studies to undergrad students to high school studies. And I think the branch and bound is a classical example of this brilliant idea that is so efficient and simple that we can even explain it in a talk these days, right?
Yeah.
I think that's all right. I think we're getting to the end of this amazing public lecture, I should say. I'm really honored to be here hosting. Would you like to say any final words, Alison?
Well, just I'd say keep up the mathematics and also keep up collaboration. I read a recent sort of paper where it came out that Einstein had a lot of collaboration when he was doing his work, and I'm strongly in favour of that. And I did miss it when I came back to Melbourne, after being with that lively group at LSE. I did miss not having anybody to sort of talk with. It's much better if you could sort of cross catch and say, well, what do you think? How do you go about this? So.
Thank you, Alison. In the name of all of us, I'd like to thank you very much for coming here today. Kate, any final words?
Oh no, just to say what an honor it was to be able to try to explain and try to do justice to the amazing work that Ailsa and Alison did, and yeah, I echo your words, Alison, about the importance of collaboration. I think the importance of collaborating with industry as well. They have some juicy problems that we can help tackle, and I think I'm pleased to say that maybe we've evolved a little bit. I don't hesitate to put my first name on papers, so maybe the world is a bit better for female researchers than it used to be.
Yeah, and with these two role models that we have here, hopefully many more women. And I would say, like, the role models are not only for women. I'm talking here to two of my own role models in mathematics, and it's an immense pleasure. So with this, I'd like to end this ACEMS public lecture, just reminding that the next lecture will be of Professor Matt Wend on Thursday, the 28th of October at 12 p.m. Thank you all, and enjoy the rest of your day.